This is Dr. J. Mohan. Today we are going to discuss about the time and frequency convolution theorem of linear time invariant LTI system in the subject of signals and stochastic processing. Today topic is time convolution theorem as well as a frequency convolution theorem in the system domain. Now we know as per the LTI system, linear time invariant system, the system response is represented as a h of t. How the h of t is going to represent? So we given for the input is x of t. It's doing for the system response, that is t into the square bracket of dot. Its producer output is y of t. How the y of t is going to produce? Now, in this case, I take for the LTI system as usual the system response condition we studied. The input is represented as del of t. Now, what I am doing, the system performance is represented as t of dot. This one is represented as y of t. Now, we given here is a x of t. This is represented as t x of t I wrote. So, this is represented as a system response of continuous time signal y of t. Now, the y of t is equal to the system response. What we are going to given for the input is represented as a x of, so it's represented as a t of del of t I represent. As the state, the LTI system, when we give for the input signal as an impulse response, then the output or system response function we call for the h of t. So now what will be happen when we going to give the input of continuous time signal in the case of LTI system, its produce the output is y of t. The system response is represented as h of t. Now I may remodify for our case. So we given for the input, then input is represented as x of t as a continuous time signal. The system response is represented as h of t. Then its produced output is equal to y of t. Now the y of t is equal to x of t into h of t. So this means what will be happen? Now we studied for the del of t. We know the del of t is equal to 1 when t equal to 0, 0 otherwise. So this means when the t is equal to 0, it is going to active. Now we can compare with this del of t into the system response of LTI cases. So when the t value equal to 0, x of t in the case, t value equal to 0, the h of t is getting to activated. That means what the t value of 0 in the x of t, some for example is 3 is there. The t value is represented as a h of t condition is represented as a 1. Why? Because of we represent for the amplitude is equal to 1. So its produced output is represented as a 3. For example, we taken. So that means each and every value of t, if we are going to shift, the h of t is getting to response. So that's why the finally we called for the LTI system, we given for the input as x of t as del of t. The system for response is represented as a y of t equal to x of t into h of t. This is a normal case. Suppose the signal is represented as a time invariant condition, as a linear time invariant condition. What's a time invariant condition? As per the statement of time invariant condition, if you take for the x of t, it's going to given the output of x of t if you are going to shift t minus of capital letter T. T minus of capital letter T. Then the system is represented as a LTI system. If you are going to shift that any time period, that capital letter T is represented as a constant, as a real constant, or time shifting constant. So then the system is represented as a time invariant system. Okay. So now I take for the time invariant system condition. Now in this case, I'm going to give for the input as x of t. So the x of t is represented as a del of t minus of capital letter T. We may represent the output is represented as a y of t. The system response t into square dot. Now what will be happen the output? The output also is represented as a x of t into h of t. X of t into h of t. This is a way we may represent. Now the signaling condition. Now we given for the x of t as a signal. It's going to doing for the system response. We given for the signal as a x of t. System response is represented as a time invariant condition. That means t of del of t minus of capital letter T. Then its produced output is represented as a y of t. So this y of t I can write as the case of input condition in the state x of t is equal to integration of x of tau del of t minus of tau dt. I will write here. So x of t is equal to integration of x of tau del of t minus of tau d tau. We may represent like this one. Now this is represented as the input condition in the case of multiply with the signal of del of t. Now this signal we going to give for the input here, time invariant system. Now I take for the LTI system. Input is represented as a x of t is equal to integration of minus into plus into x of tau del of t minus of tau d tau. I should give as a input. So here we get the output, that is y of t. So what kind of y of t we get? Then y of t, we know y of t is equal to t of x of t. That is represented as a system function. Now y of t is equal to t of y of t, that is t is represented. So this is integration of minus into 2 plus into x of tau del of t minus of tau d tau. I should write. So now what will be happen? This t, it will be going to put in the inside. I take it out for the integration is represented as a minus into plus into t x of tau del of t minus of tau d of tau. I should write like this one. So now the integration of minus into plus into t x of tau, there is no changes. Then t del of t minus of tau, it will be happen d tau. So now this one I should write as a h of t minus of tau. I make to write for the h of t minus of tau. Now the LTI system, what will be doing? Minus into plus into t x of tau doesn't get to change. There is no action happen for the t del of tau. But here only is going to time shifting is going to happen. That's why I write as a h of t minus of tau d tau. This d tau is going to happen. So this insists of t into del of t minus of tau. Why? Because of the system response. Here what I am going to say, the system response mostly it's going to happen for the del of t condition only. Del of t and t equal to 1, it's t equal to 0, otherwise it will be, and the t equal to 0 condition only, the system is going to respond as a, if you as a band pass filter condition, band rejection condition, or any filter or any condition of system response. The del of t, if you take for the LTI system in the condition del of t equal to 1, when t equal to 0. So due to that case only I should write as a our equation as like this one. This is y of t. Now this equation is represented as a continuous time signal convolution cases. So it's present for the minus into plus into in the integration x of tau h of t minus tau d tau. This is h of t minus tau is the system response of LTI condition. Now I redraw for our system function as this is x of t. We given the system function is h of t minus of tau. Its produced output is y of t. Now what is the y of t? The y of t is equal to x of t is a convolution of h of t minus of tau. We may write, or we can write for the x of t h of t. This is a convolution. So instead of h of t minus 2, I should write for the convolution. So when we do for the LTI system in the system response, it's produced for the convolution sum. That will be studied in previous case. Even though while we go for the time response as well as a frequency response, we need to know how it will be going to respond. Now this is called for the convolution sum. Okay, convolution sum as a signal. Now we go for the time convolution theorem. So this equation we derived for as the condition of LTI system. That equation that is represented as a system response we derived. The convolution time convolution theorem. The convolution of two signal x of t and h of t is defined as y of t is equal to x of t into, that is represented as a convolution. If the star is called for the convolution, h of t is equal to integration of minus into plus into x of tau h of t minus tau d tau. Now we can represent by the statement of time convolution case. The time convolution theorem state that the convolution in time domain is equal to multiplication of that spectrum in the frequency domain. This is represented as a convolution theorem. So in the time domain, we should do for the convolution, its producer output is represented as a frequency domain that will be made for the multiplication of signals. It's called for the time convolution statement. Now I take for the two signal. One is x1 of t. I take for the Fourier transform. It's produced for the capital letter x1 of omega. Another signal I take for the x2 of t. It's made to do for the Fourier transform. It's produce the output is represented as a capital letter x2 of omega. These two signal I taken x1 of t as well as x2 of t in the continuous time state. Its produced output is represented as x1 of omega and x2 of omega. As for the time convolution theorem statement, if you make to do for the convolution in the x1 and x2, that is x1 of t convolution of x2 of t, take the Fourier transform, it produces a frequency domain as multiplication of two spectrum signal, that is x1 of omega into x2 of omega. Dot is represented as a multiplication. Star is represented as a convolution. Now we do for the proof. So as per the statement, x1 of t convolution of x2 of t, x1 of t convolution of x2 of t, it's a Fourier transform is produced, the output is x1 of omega multiplication of x2 of omega. Now we take for the Fourier transform of each signal, that is x1 of t of Fourier transform is equal to integration of minus into plus into x of t e power minus j omega t dt. This is represented as a Fourier transform of input signal. Now what we are doing, I do for the input, instead of input, I am going to apply for the two input as a convolution, x1 of t convolution of x2 of t. We substitute here instead of x1 x of t, we should substitute x1 of t convolution of x2 of t. So to here, so now we substitute. So here also have the x of t, then this one, that is x1 of t convolution of x2 of t, we can substitute here e power minus j omega dt. For the definition of convolution, see what we happen for here, we taken for the two signal, that is called for the x and h, we taken. If we do for the convolution, it's produced for the y of output is equal to y of t is equal to minus into plus into x of tau h of t minus tau d tau. So here taken for the h, that's why we write for the h here. Now we taken for the t, x value, the two input, that is x2, then x1 is one input. Instead of h of t, I write for the x2 of t. We make for the convolution, it's produce output as integration of minus into plus t, x1 of tau, x2 of t minus tau d tau. Now we can substitute this one into our Fourier transform signal. So integration of minus into plus into, again integration of minus into plus into x1 of tau, x2 of t minus tau d tau, e power minus j omega dt. So this purpose only, this equation purpose only, we derived for these values. The y of t, system response, y of t is equal to minus x of tau, h of t minus of d tau. So due to that purpose only, we done for this, the derivation, e power j omega t dt. Now we may rearrange the integration. So minus into plus into x of tau, you take it out, we consider as a constant, we take it out, x of 1 of tau. Another integration minus into plus into x2 of t minus tau, e power minus j omega t dt, and d tau is there. Now instead of t minus tau, I take for the u values. T minus tau is equal to u value. Then what is that? Here is going to have the t. So t minus tau is represented as a u. This t, what we represent, t is equal to u plus of tau. Instead of this equation, t, this value I need, then tau is go this side, that is u plus tau. U plus tau is going to happen. Now you take for the here is represents the dt is there, then you take for differentiate with t, dt is equal to du. Tau is not getting because of a constant, dt is equal to du. Then you substitute all this value and this value and this value into this equation. So integration of minus into plus into x1 of tau, integration of minus into plus into x2 of t minus tau, e power minus j omega t dt d tau. So t minus tau is substituted for the u. Then t we substituted for u plus of tau, dt is substitute du. Now we may again rearrange. Integration of minus into plus into x1 of tau, integration of minus into plus into x2 of u, e power minus j omega u du. So all u terms for here in this case, all u terms take it out. Then remaining term, e power j omega tau d tau, we take it out. Then what is it? This value is represented as a capital letter x2 of omega. I write for the capital letter x2 of omega. You take for the Fourier transform signal. What is the Fourier transform? The Fourier transform of x of t is equal to minus infinity to x of t e power j omega t dt. So instead of t, here will be going to have the u. That's it. So we take to write as x2 of omega. Then e power j omega tau d tau. For this one is represented as a x2 of omega, capital letter x2 of omega. Is it? Then take it out for the x2 of omega from this equation. x2 of omega remaining, integration of minus into plus into x1 of tau, e power minus j omega tau d tau. All it's in the tau case. Then this is equal to Fourier transform equation. So here is x1 is a, then we represent as a x1 of this value, x1 of omega. Now what will be happen? If we do for the time convolution in the Fourier transform, take for the two different signal x1 of t and x2 of t, it's produce the output is represented as a multiplication of that two signal in the frequency domain. So I write for the statement x1 of t convolution of x2 of t, Fourier transform is equal to multiplication of frequency domain in x1 of omega into x2 of omega. If we do the convolution in the signal state of Fourier transform, its produce the output is multiplication in the frequency domain. This is expression is known as time convolution theorem. Next, we go for the frequency convolution theorem. First is to go for the statement. The frequency convolution theorem states that the multiplication of two signal in time domain is equal to the convolution of the spectrum in the frequency domain is represented as a frequency convolution theorem. Now in this case, if we multiply for the two signal in the time domain is equal to the convolution of the spectrum in the frequency domain. Previously, what will be happen in the time convolution state? If we convolution of two signal, the frequency state it's getting to multiply in the Fourier transform. Now frequency convolution, if we multiply for the two signal, in the frequency domain it's getting to convolution. So this is represented as a frequency convolution state. Now if we need to explain for the frequency convolution statement, we take for the two signal x1 of t as well as of x2 of t. You take for the Fourier transform is represented as a x1 of omega as well as of x2 of t in the Fourier transform is equal to x2 of omega. The frequency convolution statement represented as a multiplication in the time domain x1 of t into x2 of t. Take the Fourier transform. Its produced output is represented as a convolution of in the frequency domain x1 of omega convolution of x2 omega divided by 2 pi. This is the mathematically representation of frequency convolution theorem. Now we go for the frequency convolution theorem proof. From the definition of Fourier transform, we write for the f of x of t is equal to x of omega. The value is equal to minus into plus into x of t e power minus j omega t dt as a formula statement. Now I take for this x of t is equal to, I multiply with two signal x1 of t into x2 of t as the frequency convolution theorem statement. We multiply for this two. Instead of this x of t, we should substitute for this value. Now the f of x1 of t into x2 of t is equal to integration of minus into plus into x1 of t into x2 of t e power minus j omega t dt. From the definition of inverse Fourier transform, as a inverse Fourier transform definition, the formula is represented as a f inverse of x of omega is equal to x of t. So that's why we write as a our Fourier transform x of t as double arrow mark, that is for this side reverse arrow mark and forward arrow mark of Fourier transform is equal to x of omega. If forward as a frequency Fourier transform is going to spectrum. If we take for the spectrum as a inverse, that is a f inverse, then we get for the x of t. So due to that condition, x of t is equal to inverse Fourier transform of x of omega equal to 1 by 2 pi integration of minus into plus into x of omega e power j omega t dt. For as per the Fourier transform condition, I will write for the equation for here, that is x of omega is equal to, for the x of omega, integration of minus into plus into x of t e power of minus j omega t dt. So this is the omega, that's why it's going to take for the differentiate with the t with integration of t. Here we need for the t, we need for the x of t condition in the inverse condition. The frequency spectrum is going to taken for the inverse Fourier transform. So here is omega is there. You should write for all term in the omega condition. That is input is omega, x of omega, e power, here is plus, instead of plus you take for the minus, t is there for the t domain, omega domain you write for the d of omega. This is the way is represented for the inverse Fourier transform. Now we take for the inverse Fourier transform of x of t. We need to substitute for this equation. What the equation? Our convolution cases. That is convolution cases of frequency domain. That means it's represented as a multiplication. Now we do for the multiplication here. That is integration of minus into. So instead of any one of the t, here I take for the x1 of t. x1 of t is represented as 1 by 2 pi as the inverse Fourier transform 1 by 2 pi integration of minus into plus into. All terms are t, that's why I take for the p term x1 of p e power j pt d of p, then x2 of t e power minus j omega t dt. Now, by rearranging the order of integration, then f of x1 of t into x2 of t as a statement of frequency convolution case equal to 1 by 2 pi integration of x1 of p. I take it out for the x1 of p in outside and 1 by t also take it out for the outside. Integration of minus into plus into what the remaining is that x2 of t e power minus j omega t e power j pt dt dp is there. Now these two term you can simplify. What we are waiting as for the f of x1 of t into x2 of t is equal to 1 by 2 by integration of minus into plus into x1 of t integration of minus into plus into x2 of t e power minus j omega minus p t dt and dp is there. Now you can see here this is represented as a shifting property of frequency domain. So as per the statement of Fourier transform, the x of t is time domain case. If you need to convert for the frequency domain, x of omega is represented as a integration of minus into plus into x of t e power of minus j omega t dt. What the terms present for the omega, we write it for the x of omega. Suppose this term for here, due to this term, here omega minus of p is there, then here we write for the x of omega minus p. So see, integration of minus into plus into x2 of t e power minus j omega minus p dt dt dp. So this term I should write as a Fourier transform of x2 of omega minus of p dp. This dp I write, this term I write x2 of omega p. Now 1 by 2 pi integration of minus into plus into x1 of p x2 of omega minus p dp. We got it. See this equation. What is this equation? This represent as a signal convolution condition. So what the signal convolution? If we take for the x of t as a LTI system condition, the signal is getting to convoluted. Okay, what the case? X of tau, h of t minus of tau, d tau. So this one we write as a x of t convolution of h of t. That means is represented as a y of t. Now the system response as a LTI system is taking the input given by the shifted version of del of t minus of tau. It's a produce the output is represented as a y of t. This y of t is depends upon the shifted version of input. So now the shifted version of input, what we are going to write like this format: integration of minus into plus into x of tau h of t minus tau d tau. Then only is possible for the LTI system. If you do for the LTI system in the system signal convolution, it's multiplied with the two signal. What are the case? The system response y of t is equal to x of t convolution of y of t. Now we use for this term to simplify for this equation. So we got for the x1 of p, x2 of omega minus p dp. This is a shifted version of omega p. That's why f of x1 of t into x2 of t in the frequency domain 1 by 2 pi I should write x1 of omega convolution. Due to this equation I represent the convolution of x2 of omega. Then x1 of t into x2 of t Fourier transform if we take 1 by 2 pi x1 of omega into x2 of omega. This value I represent as a convolution. So the convolution frequency convolution theorem in the radian frequency I should write as a x1 of t into x2 of t in the time domain. Take the Fourier transform is write as a frequency domain. This is a spectrum domain. It's a frequency domain x1 of f convolution of x2 of f. Now f is equal to omega divided by 2 pi we represent. Up to this much I am going to conclude my section. So frequency convolution as well as time convolution, this section we discussed. At the same time how the signal it will be going to generate as a signal convolution state. Thank you.
Like, share and subscribe. hit the bell icon for more updates.